Okay, we have seen before in the previous video that a displacement current is present in the capacitor, and because of this displacement current, then we get a magnetic field. Okay, so together the displacement current and a conduction current, they make a continuous current in the circuit. All right, so now we will discuss about the magnitude of the displacement current. Okay, now look here. This ID, it is present only just inside the capacitor. Okay, outside the capacitor, it is the current IC. Okay, so if E, let's say it is the electric field which is present in the capacitor, then we know that this electric field between the pilot plate capacitor is equals to sigma upon epsilon naught. What is sigma? Sigma is the surface charge density, and this epsilon naught, it is known as the permittivity of free space. Okay. Now, but sigma is equals to how much? If the charge in the capacitor, let's say the charge here it is Q, then the charge in the capacitor is Q, so charge present per unit area. What is A? A is the area of the plate of the capacitor. So sigma is equals to Q upon A. So therefore, putting the value of sigma above, you will get E equal sigma, you'll get Q upon A epsilon naught. Or, taking A to this side, you'll get EA is equals to Q upon, okay. So you transfer A epsilon naught left hand side. Right hand side, you'll be having only Q. Okay. Now, if you differentiate both sides of this equation, then you'll get, okay, so before that, let me do like this. I missed one point. Okay, what is EA? EA, electric field times area. Electric field times area is electric flux. Okay, because we know electric flux is equals to EA, just like magnetic flux is equals to BA. So EA is equals to electric flux. Okay. Now, if you differentiate this equation both sides with respect to time, then you will get ddt of phi E epsilon naught, and right hand side ddt of Q. Okay. Since epsilon naught is constant, so I'll take it out. So inside I will have only ddt of phi E. Okay. And right hand side. Now, dq upon dt is equals to I. Now, what I is this? Is it IC or ID? The answer is ID, because it is the current, right? Inside. Here we are considering inside the capacitor. So this is the magnitude of the current, of the displacement current inside the capacitor. Okay. So again, right from here, I can say that this d phi upon dt is the rate of change of electric flux. So when the electric flux inside the capacitor is changing, it means the electric field is varying. So that varying electric field creates a displacement current. And this displacement current will in turn produce a magnetic field. So hence I can see here that it is not just only the conduction current that produces the magnetic field, but even the varying electric field can also generate magnetic field. Okay, so this is the displacement current. Now, if this is the magnitude of the displacement current, then Maxwell, the modified form of Ampere's law becomes line integral of B dot dl is equals to mu naught IC plus ID. Or I can say this is equals to mu naught, instead of, okay, this is IC, fine, I multiply like this, plus mu naught times ID. Okay, or the line integral of the magnetic field around any closed loop should be equals to how much? Now putting this ID, which is equals to epsilon naught d phi e upon dt. So this is now the final modified form of Ampere's equation. Okay, now this term here, mu naught epsilon naught, just epsilon naught d phi e upon dt, it should be having the same dimension as current, or the same unit of current. Alright, so this is all about the magnitude of the displacement current and the modified form of the Ampere's circuital law. In the next video, we will discuss about the Maxwell equation, and those equations are very important because, as I have already said right in the beginning of this unit, in the beginning of this chapter, that with the help of those Maxwell's equation, then we get an electromagnetic wave, and that electromagnetic wave, we will show later that they are a transverse wave, which consists of varying electric and magnetic